All right, let's jump right in. Today we are tackling one of the biggest, most mind-bending ideas in all of physics, string theory. And really, it's a story. A story that tries to answer the most fundamental question we could ever ask. I mean, how do you even begin to answer a question that big? Well, for as long as we've been human, we've done it the same way. We tell stories. We create these incredible explanations for how the world works, from ancient myths all the way to modern physics. And that's really what science is, isn't it? It's a process of telling a story, testing it against reality, and then refining it. We keep the stories that work, and we toss out the ones that don't. But sometimes the stories that seem to work get really, really weird. And that brings us to the fascinating and pretty controversial story of string theory. So, our story really kicks off when we started exploring the absolute smallest layer of reality, the world of elementary particles. We smashed atoms together and found these tiny little bits that just couldn't be divided any further. But this amazing discovery came with a huge, huge problem. We couldn't actually see them. Think about what it means to see something. It's not a passive act. You're literally bouncing light off an object to get information back. Now, to see something as tiny as a particle, you need a light wave that's small enough to hit it. But here's the catch. The smaller the wave, the higher its energy. So looking at a particle is kind of like trying to figure out where a billiard ball is by smashing another one into it. Sure, you'll find it, but you've also just knocked it clear across the table. The very act of looking at it changes it. And this isn't just a problem with our equipment being clumsy. Oh no, this is a fundamental rule of the universe. It's called the Heisenberg uncertainty principle. And it basically says there is a hard limit to what we can ever know about a particle. The quantum world is, by its very nature, inescapably uncertain. Okay, so if reality at its most basic level is totally fuzzy and uncertain, how on earth could physicists do any science at all? Well, they did what we humans do best when we hit a wall. They got creative. They invented a new story, a very clever workaround. I absolutely love this way of putting it because it gets right to the heart of how science makes progress. It isn't always about finding some ultimate, capital T, truth. A lot of the time, it's about creating models that are useful and that make accurate predictions. And the model they came up with, it was a truly brilliant piece of fiction. They just decided to pretend. They said, okay, we know an electron is actually a fuzzy cloud of probability, but for our calculations, let's just pretend it's a perfect, single, dimensionless point in space. A little dot that has specific properties, like a certain mass and a certain charge. Now, they knew it wasn't really a point, but this assumption, this little fiction, it allowed them to build equations that actually worked. And just how well did this fiction work? Unbelievably well. The predictions made by treating particles as points have been tested and found to be accurate to 0.00000000002%. That is just an insane level of accuracy. This fiction is the bedrock of the standard model of particle physics. It's behind most of the technology we use every single day. It is a fantastically successful story, but it has one fatal flaw. There was one gigantic piece of reality that this beautiful, successful story of point particles completely failed to explain: gravity. And this created the single biggest conflict in all of modern physics. See, you've got two different stories for the universe. On one side, you've got Einstein's general relativity. This is the story of the very large: planets, stars, galaxies. It says gravity is the fabric of space-time itself. It's the stage where everything happens. And this story requires everything to be perfectly smooth and precise. But on the other side, you have quantum mechanics, the story of the very small. It describes all the particles as actors on that stage, and its fundamental rule is uncertainty. The two stories just do not speak the same language. They're totally incompatible. And when you actually try to combine them, when you try to describe gravity on the quantum level using that idea of a point particle, the math completely falls apart. It just spits out nonsense, like infinities. This is a huge deal. It means our understanding of the universe is fundamentally incomplete. We need a new story, a theory of everything, that can finally unite these two worlds. So some of the smartest people on the planet started hunting for that news story. They went all the way back to the beginning, back to the problem with the point particle, and they asked a really, really simple question. Just think about that for a second. A point has 0 dimensions. What's the next step up? What has just 1 dimension? A line. Or a tiny vibrating string. And this simple, almost obvious idea was the birth of string theory.
The core idea is just so elegant. It says that if you could zoom in on an electron way past any level we can see, you wouldn't find a point. You'd find a tiny, one-dimensional loop of energy, a little string vibrating.
And this is where it all clicks together so beautifully. Think about a violin string. By vibrating in different ways, it can create a huge range of different musical notes, right? Well, string theory says a fundamental string works the same way. One pattern of vibration makes it look like an electron to us. Vibrated a different way, and it looks like a photon. And this is the crucial part. Another specific vibration gives you the particle for gravity. For the very first time, a single idea could explain all the particles and all the forces. It was like discovering the music of the universe, and it was all being played on one tiny type of string.
I mean, what an incredible idea, right? String theory promised to be the theory of everything, the final story. But as it turns out, our proposed hero has some pretty serious flaws. It comes with a lot of, well, strings attached.
First, for the math to hold together without breaking, string theory requires the universe to have 10 dimensions, 9 dimensions of space and 1 of time. We only see 3 spatial dimensions, so theorists have to come up with these really complicated ways to explain where the other 6 are hiding. So far, no one's managed to do it in a way that actually describes the universe we live in. And then there's the biggest problem of all. There is not a single piece of experimental proof. It hasn't made a single prediction that we can actually go out and test.
So if it's untestable and it doesn't even describe our universe properly, you might be wondering, why are we even talking about it? Why is it still one of the most active areas of research for physicists? Because, just like that point particle fiction, it turns out to be an incredibly useful story.
Here is a great analogy. Imagine you want to build a massive cruise ship. That's our theory of everything. But you don't know how. All you have are the blueprints for a small rowing boat. That's string theory. Now, a rowing boat is not a cruise ship, but they both have to do the same fundamental thing: float. By studying the simple principles in those rowing boat blueprints, you learn fundamental truths about buoyancy and hydrodynamics that will help you eventually build that cruise ship. And that's string theory. Its math works, and it lets physicists explore really tough questions about quantum gravity and black holes in a way no other tool can. So no, string theory probably isn't the final story of everything, but it is a priceless tool. It's a powerful mathematical story that is helping us ask better questions and is pointing us in new directions in our quest to understand reality. It's an essential stepping stone.
And that brings us right back to where we started. The history of science is a museum of useful stories, each one leading to the next big thing. The search for the true nature of reality is absolutely still on. The only question left is, what incredible story will we come up with next?